Alright, so for this particular video, I have a few MCQ on simple harmonic motion for you to practice. If you need to, pause and read for this first one. But essentially, you have a vertical spring that's been stretched down some amplitude A, and you're going to release it. And by the time the block has traveled a distance of A over 2 on the way up, it took some time, lowercase t. And the particular question wants to find the period of the oscillation. So here's an animation for you to help visualize. On the left side, you have a spring, and then all of a sudden you're going to pull it down and then you let it go. So the problem here starts at negative A, and then it's going to move upward and then stop and then come back down to where it was. Okay, so this particular graph traces out a cosine function. So here my y of t, this is y of t just because it's in the vertical direction. If you want, you can keep it as x of t, it doesn't really matter. The more important thing is on the right side, whether it's sine or cosine. So y of t here is going to be a cosine omega t. I'm just going to replace y of t with a over 2 because that's what the problem states. And then a is just the amplitude of the oscillation, which is just a in the diagram. And then omega, I just broke up into 2 pi rad over capital T. I did this because the question asked for capital T. The word period hopefully should trigger capital T because that's what capital T represents in harmonic motion. Okay, so here I'm just going to cancel out a on both sides. And then I'm just going to clean it up. So the left side is just 1/2 a, and then on the right side is just cosine 2 pi over capital T, the period, times lowercase t, whatever lowercase t is for this one. Now, at this point, it's important that you do correct algebra in order to get capital T by itself. Again, capital T is what you're looking for. So to get rid of cosine, I have to do cosine to negative 1 on the left side to get rid of the cosine on the right side. So it'd be cosine to negative 1 of 1/2, and on the right side, everything in the parentheses just gets carried down because I haven't done anything to it, right? So it's just 2 pi over capital T times T. So at this point, I'd like to remind you that your calculator needs to be in radian mode, not degree mode. So here, if you punch in cosine of negative 1 of 1/2 on your calculator, you just get about 1.0 something. But if you know unit circle, I'm just going to go ahead and say that's pi over 3. Okay, I kept that as pi just because I know just from experience that there's a 2 pi here, and then that's going to cancel out the pi on the right side. So here I'm just going to clean it up. I'm going to cancel out the pi's on the left and right, and then to get capital T by itself, I'm going to multiply both sides, or I'm just going to move the capital T to the top left. But you notice here there's a 3 on the bottom left here, so I'm going to get rid of that by multiplying both sides by 3, or I can just move this 3 to the top right. So just do your algebra. So if you do your algebra correctly, you get T is equal to 3 times 2 times T. Well, 3 times 2 is just 6, so the answer would just be 6T. Okay. Now, so if you want to think about this particular question in a math sense, this is kind of it. All right. Just make sure you don't fumble on your algebra or forget that you need to be in radian mode. However, if I was doing this question, I would just logically reason it out. Right, here's a cosine graph. Here's a positive cosine graph. I know the problem says that it's negative cosine, but really the ratio doesn't change. Cosine, negative cosine, same graph. It's just a mirror image. So I'm just going to stick with the positive cosine graph here just to teach you this skill. Well, here is some unit A. All right. So the graph here starts some amplitude, whatever it is. On the vertical here, it says the displacement of unit of A. So that's 1A, whatever the amplitude is. Well, it sets in the problem that you're going to go half the distance up or down, right? So here I'm just going to go down. And it took some time t. So here in the coordinate system here, well, how much time did it take to get to this particular junction on the graph? Some time t. Well, how far did you travel? Half the amplitude because you went from 1 to 0.5. So if you think about it, right, this is the time that it takes already to just go halfway. Well, a period is the time that it takes from amplitude, or positive amplitude, I should say, to the next positive amplitude. So here in this particular graph, I've restricted the graph to just one cycle. Well, one block is already t. The next block is another t, so that's 2t. The next block, that's another time, so that's 3t. And this is 4t, and then this is 5t, and then this is 6t. So really just by really, thinking about it, you know that the answer is 6t just because the ratio here for every half, which is nice, symmetrical, is one block. Okay. All right. I hope that helps. If you need to, rewind it and listen to it again. So the answer is 6t just really just by looking at a cosine graph. All right. Let's move on to the next one. The next one is this one. Here you have a mass on a spring that bounces up, so forth. And then it says the y of t function is given as 6 sine t. All right. And it wants to find the rate at time to go to 5 seconds. So you notice here all the answers in centimeters per second. So the word rate here would just imply that we're just trying to find the linear speed or linear velocity. Okay. So I'm just going to go ahead and start with the function I'm given. Y of t is equal to 6 sine t. So you notice here, there's no omega in this parentheses. well, there's no omega because omega is 1. So really it should be omega t, right? But when you don't see an omega, you would assume that omega is just 1 because 1 times t is just t. So these are little tricks that you have to pick up if you're doing simple harmonics for an exam. All right. So here I'm just going to take the derivative of y of t because it asks for v of t. So v of t is the derivative of y of t. And then here I just put 6 sine of t in parentheses. So you have to make sure you apply chain rule for these particular harmonics derivatives. So the derivative of sine is just positive cosine. So if you don't know your sine and cosine, this is just a quick review, hopefully. So here in the first statement, the derivative of sine is a positive cosine. So I'm just going to do that. So the derivative of y of t with respect to time is going to be 6. That's the 6 that gets carried down. And the derivative of sine is just cosine, and t stays the same. However, you also need to take the derivative of t, but the derivative of t in this function is just 1. So I'm still not going to write the 1 because 1 times anything is just itself. All right, but don't forget to make sure you apply chain rule correctly. All right, so other than that, it wants us to find the velocity at 5 seconds. So here's my work is v of t is equal to 5, and I'm just going to plug t for 5. And if you do this correctly on your calculator in radian mode, you'll get 1.7, which match answer choice A. All right, let's move on to the next one. This one I think is a bit more interesting. So if you need to pause, read. Essentially, you have a simple pendulum, same shape, except the second scenario says that the object has a greater density. Okay, so if you know your harmonics function, I'm just going to start with this. I'm going to start with this because the first column has to do with the word period. Period here is 2 pi the square root of L over G. Well, the length of the string hasn't changed, so therefore the period must stay the same. Okay, so I'm going to cross out a couple of things here for you. I'm going to cross that out, and I'm going to cross that out because I know that the question states that it's only the density that changed. So the length of the string hasn't changed, so therefore the period of oscillation must stay the same. So if L stays the same and G is a constant, T must be the same. And I made a note for you here. This is independent of mass. So why the object has a greater density, you know, it has nothing to do with mass or volume. Okay, so let's move on. Let's move on to KE. The second column here has to do with the word or the concept kinetic energy. So if you know, kinetic energy is just 1/2 mv squared. But this is an object that has the same shape, but it's denser, you know, so it has more mass because density is mass over volume. So I'm just going to go ahead and introduce this for you if you haven't seen it. Density equals mass over volume. Well, same shape would imply the same volume, but if you have more density, that would imply that mass also has to change. So I just made a comment here for you. I'm going to solve for m, all right? And then I just said here, if mass goes up, then density has to go up and vice versa. So if you think about it, the problem states that it has a greater density. So if density here, rho, is greater, same side would imply volume stays the same. Well, if density goes up and volume stays the same, then the product on the right side, or the quantity on the right side, has to also go up. So in this case, the mass went up in order to give you more density. Well, KE depends on mass, so I made again a deduction here. If mass goes up, then KE also has to go up. So therefore, KE cannot be the same. So I'm going to cross that out. So right away, with just these two concepts, I can cross out what the first 3 answer choices, right? The period can't be the same. It can be larger because it has to stay the same, and it can be smaller. And then here in KE, well, it can't be the same because the mass went up, because density went up. So it can't be the same. All right, so just by those two, you notice that the only answer choice I haven't crossed out is the very bottom one for this particular example. So if you want, you can go ahead and do maximum acceleration as well. So to do maximum acceleration, you just apply Newton's second law, net force equal to ma. So here is the visual for you. This is a simple pendulum. The tension is pointing along the line of the string, and the string here is capital L, the length. And then here, I would treat this particular problem like an incline. You have f of g pointing down, and you have f of gx and f of gy. However, the only thing I need to focus on is f of gx, which is mg sine theta, because that's the acceleration in the tangential acceleration, or the direction. All right, so this is the y-axis, this is your x-axis. So if you treat it like an incline, you can kind of see that it plays out. Well, what force is accelerating this particular mass as it swings? That's going to be f of gx because it's in the line of motion. And then here, f of gx is just mg sine theta. Mass cancels out. And then really your expression here is just ax is equal to g sine theta. right? So A here depends on theta. So as theta changes, A changes. So as an object swing, the angle, either gets smaller or bigger depending on which way you go. But the point is that as theta changes, A also changes. But for this particular question, theta didn't change. It's saying that the only thing that changes the density of the object. It got released from the same angle. Well, if theta stays the same, then A stays the same, right? So therefore, I made a note here that it's independent of mass. Okay, so while the density of the object goes up, it doesn't affect A because I cancel out mass in my work. All right. Other than that, just by deduction, I think already without touching acceleration, the answer is the bottom answer choice. Okay. Let's move on. The last one of this one is this one. If the length of a simple pendulum is quadruple, its period will, and here your answer choice is A, B, C, D, E. So here is a animation for you to follow. As you can see here, there are 3 objects on different lengths or that have different lengths of string, and just by looking at it, you can see that the one with the longest string, takes a while to go there and back, right? So I'm just gonna apply the function I used earlier in this video. For a simple pendulum, the period is equal to 2 pi square root of L over G. But as you can see here, the length of the string got quadruple, so I'm just gonna do this twice. Oh, by the way, I want to cross certain answer choice out just because I know the answer choice cannot be. L is in the numerator, so I want to cross it. It can't be the same because if L changes, T changes, and then L is in the numerator. So if L gets bigger, the period also has to get bigger. So I'm going to cross C, D, and E out because these answers makes no sense, at least for this particular problem. Okay, and I'm just going to apply it. So here's my T new. T new is the same function except instead of L, I'm just going to replace it with 4L because the problem said so, and then without overcomplicating it, you can just pull out the square root of 4 here, and then 2 pi times radical L over G is just the original time, and the square root of 4 is just 2. So the answer here would just be that it would double. Okay, all right. I hope that helps. Stay nerdy, and we bye.